nanohub.org.
Online simulation and more for nanotechnology.
So today we'll continue this discussion about data analysis and related to design of experiments. I promised that I will be explaining a few more topics that I couldn't cover well in today's lecture, but I thought that today's lecture is so intimately connected with the previous lecture that I want to delay that discussion till next week. But I want to start with this this specific things, and the title already tells you that there is it's going to be very interesting, that that this is going to be equation free. Or even when you don't know the equation or don't know physics, it turns out that you can do a lot of things to reduce the number of experiments you have to do. So that is the goal of this lecture. So you may remember that the way to reduce the number of experiments is that many experiments variables don't really don't have the effect on the final result in isolation, but what they have is that they come into a combination, a dimensionless combination. So today, but we needed an equation last time. Today I will explain to you that how even without equation you can do a lot. And after today's lecture, you will begin to understand that how before the Maxwell's equations were around, people could already explain why the sky is blue, because that was before Maxwell's equation came along. And even if Maxwell's equation there, you could not really explain it. How Newton already anticipated Einstein, all because and how Wright brothers, before they could know how to do fluid dynamics and solve the fluid dynamics, the Wright brothers could already design aeroplane. If you go to Iowa, what is the Wright brothers museum is, I think in Ohio. So you can see in it full display, and you'll be amazed. In the beginning, it looks like a magic, but my goal is to explain at the end of the lecture why there's nothing called magic. There's always a reason why something works. So the main goal today would be for me to explain this something called a Buckingham PI Theorem. And the Buckingham is the name of a person. Actually, it turns out that this particular way of viewing experiments have been around for almost 30-40 years before Buckingham formalized it. But many scientists have been using it. And that's how they were able to astound people about their predictions. So the pi is just a mathematical symbol pi. So we'll see that. I will work out 3 examples to make you comfortable, and then I will explain to you why does the method work. How is first, how the method works, and then you will see why the method works. That will be my goal. So let's start by a problem definition. Let's say you are somebody who is from 18th century and you do not know how something degrades. You do not know. But you have an intuition that it will depend on the temperature. You don't have any equation, but you have intuition that higher temperature. And let's say you know that the materials which are stronger, they have longer lifetime. So EB is sort of it could be atomic bonding, or it could be the strength of the material, some characteristic of the material, which are, let's say, strong. And then you may also think that this is a thermal problem, so maybe Boltzmann constant would be important. And let's say you don't even know whether quantum mechanics has not been invented, h bar is, but you say you put some dimensions there. In fact, it will turn out that you will anticipate the dimension h bar in a few minutes. So if you wanted to do these experiments, then you can immediately see you will have to do 100 experiments. You have to take 10 different materials, that's the proxy for EB. And EB is sort of the energy for braking. You can view it that way. It's not a quantitative measure, but let's say you have not measured it yet, but you have 10 different materials characterized by, let's say, 10 different EB. And then you also may have to have 10 different temperature, and then that will be 100 experiments. And that's something you don't want to do. So the question is that can you do better? And it turns out that you really can do significantly better even when you don't know the equation at all. You have no idea what the physics is. And the reason you will be able to do better, because very soon, given this combination of parameters, you will find that there are just two combinations of parameters which are dimensionless. And it will always come in the form of EB over KBT, and it will always come in the form of KBT over H bar. It will always come in this form because these are dimensionless. And whether this side is sine EB over KT or e to the power minus EA over EB over KT, that you do not know. That will come from experiment. But what you can immediately say, whatever experiment you are going to do, what your x-axis is going to be and what your y-axis is going to be. So today's presentation is all about what should your axes be, even if you before you go to the lab to do and look at an unknown phenomena. And so this axis will be EB over KT, not T or EB individually. And then we'll see how that works. So let me begin with that. So there is this formal definition of Buckingham PI Theorem. You can look it up in Google or in anything. I'll just read it once, but I don't expect you to understand these things until I show you a few examples. So therefore, the basic thing is that, in the last example, we had 4 parameters, T, EB, H bar, and KB. And so those are Q1, Q2, and Qn. In principle, you can have n of them. And the R that you saw, R has been pushed back on this side. So this is 0 means that you push the R in this side and write the R minus the whole thing as G, as the whole thing. So those are your parameters. So parameters may be some of the parameters you wish to measure, some of the parameters that are given input and output. And the G could be a differential equation like this for second order. And last class we said that, you remember perhaps that we had to normalize Y in terms of the time constant, and then we had to scale it, and then we could get the equation. So a G could be a differential equation that you solve given the parameters Q1, Q2. This could be diffusion coefficient, this could be recombination time, and so on and so forth. But G does not, you don't have to know that. So G could be wave data where there's no differential equation. But you may still know that what are the variables that are or you can have a hypothesis that what are the variables that are controlling things. Like people from hot country, they are hot-tempered, let's say. If you want to say that, so the temperature would become one variable. You have no equation for the human being, right? I hope not. But so it could be a black box. In the black box, and then you have some control parameters, Q1, Q2, Q3, those things are. So this is, you can beginning to see that where the machine learning and other things comes from. The basic idea is that even when you do not have a differential equation, you can still do experiments in a very clean way with the dominant variables clearly defined. So that's very strange. First time I read it, I could not believe that this could be true, but it is true. Let's say the point of this theorem is that there are some revised parameter pi, and that's where the pi comes from, this pi, Buckingham pi. The pi, Buckingham said that you can take a bunch of dimensionless parameter whose size is smaller than n, number of control variable n, and by how many smaller is the number of independent dimensions, which I'll explain in a second. And each one of these dimensions, pi 1, pi 2, pi 3, these are dimensionless variable, right? EB over KT, right? That's one dimensionless variable. So we are talking about that the procedure, given a set of parameters, the procedure to find the dimensionless combination. Now you may ask that, well, how do I know what my input things are? You guess. A good scientist always guesses. And so therefore you guess. And if you have some experience, let's say, how fast would a cup of coffee cool down? You have some experience that hotter it is, it takes longer. If the cup is bigger, then we used to pour tea in the saucer. So that enhances the area, surface area. So you will put those variables in as your input variable. Your intuition goes as your input variable. If you are wrong, this will tell you that you don't have sufficient number of variables. But if you are wrong in a fundamental way, then this will not be able to identify completely because it doesn't know physics. It just knows math. So I'm going to define all this matrix in a few minutes, this matrix, and you will often see that there will be something called a P matrix and a Q submatrix. And I'm going to define something called an exponent matrix, which will be this P inverse and multiplied by Q. And this is an identity matrix. And that, the eigenvalues associated with that will tell me what the variables are going to be. So, this is like math talk, which doesn't make much sense. So we want to see some examples first. But before you get to the examples, I hope you know that there are 7 fundamental variables. In physics, there are 7 fundamental variables. And the variables has to do with mass, length, the time, the temperature, and so on and so forth. So there are 7 scale variables. And you should be able to, any phenomena in physics can be expressed as a combination. Well, everything has a unit, right? So if you know the unit, then you can express it. For example, remember the problem I'm working with. I'm working with a problem that has EB, temperature, degradation rate, K and H bar. And EB, how much it is, if you don't remember what the unit is, you know that it is half mv squared has the same unit. Energy has the same unit. And m, therefore, has a unit of 1. So therefore, I have written m unit of 1. And v square is distance traveled per unit time. So L divided by T squared. So you have L, 2 L's and 2 T's. And then you don't have anything with the temperature. So therefore, you set it to 0. That variable is set to 0. And similarly for temperature, of course, you don't have any mass and other dependence. Only thing you have is the temperature dependence. Right? So you essentially write it up in terms of the variables, or if you don't remember, you can just look it up in the web in terms of what the units are, and then you can write it up in terms of the units. Okay, so there's nothing in here. So let me show you how this method works. Remember, so how I have to first set up a matrix, and you have to pay a little attention here to see what I do. On the top side, I have written the 4 variables, fundamental variables. Now remember, there are 7. I have not written the other 3 because the other 3 don't come in these are not necessary. So even if I had the other 3, there will be a bunch of zeros in here. So therefore, I don't have the other 3. Then these are my variables that I want to connect. So for example, you remember T, Kb and all. And you remember that when I'm thinking about temperature T, then only thing that I have is the Kelvin, is the only unit I have. That's the power. So this matrix is all about the power of the thing. I will not go into too much detail, but you can see rate is something per unit time, degradation per unit time. So what will be its unit? Unit will be inverse of time. So do you see that when there is that t-axis, I have a -1 here because it's inverse of time. And then I don't have to go through the EB and KB, you sort of can work it out. When you do that, look at this list. First of all, writing this matrix is very important because it just takes a few minutes. You quickly take, and anything you guess. You have guessed this 4, you have guessed this 5. If you like, you can throw away H, for example. And then because it's all guess, so you can write whatever you want and then start from there. It will always give you the right answer, given that assumption, what the right experiment to do. It will tell you that. So how many unknowns do I have? I hope you will say 5, because there are 5 unknowns in this problem. What is the rank of the matrix? Rank of the matrix, you may remember, this is the number of independent rows, right? Not all rows are independent, need not be all independent. One can be a scale version of the other one. So therefore, rank of a matrix is number of independent rows. So how can you get the rank of a matrix? Well, you can do it. You can just throw it. If you don't want to evaluate everything, you can just throw it in Wolfram alpha. It will tell you rank is true, or rank is 3, whatever. Right? So in this particular case, rank is 3. So that means 3 independent variables. So therefore, how many parameters am I going to have? The Buckingham PI Theorem says I have to subtract 5 from 3 from 5, and so I am going to have 2 independent parameters. You are sort of seeing, right? The final answer is going to be EB over KT, and another is going to be R divided by that KBT divided by H bar. So those are the things that are going to come out. So it's already telling me that I cannot have more than 2. And those are going to come in that combination. And so I'm going to have pi 1 and pi 2. And by the word repeating variable means that if you take some other combination, then it is going to, after you do the multiplication division, it is going to be the same 2. You can express, let's say you have a pi 3, pi 4, some other form, or pi 1 bar and pi 2 bar, slightly different combination. But then you can show that you can combine, you can take 2 and divide by each other, it will get pi 1. And you can take 2 and then multiply each other, you will get pi 2. So it's going to be the same thing in a different name. So therefore, we don't have to rewrite it in any other form. Those are all equivalent. I'll show you some examples. So you can take any non-zero determinant for P. So remember, 3 equations are independent. So I have taken 3 by 3. And what am I going to call this? I'm going to, just one second. I'm going to call this P. Now, there's no harm. You can call this one P if you like. You can call this one P if you like. But it has to be sort of, the determinant cannot be 0. Because you see, if you take these 3, then the determinant may become 0. So therefore, you cannot take that one. So whichever one doesn't have a sub matrix, which doesn't have a determinant of 0, 3 because 3 independent repeating variable, you take that one. You had a quick question.
So I didn't see the last matrix, how you got the repeating value is 3.
No, just because the rank of the thing is 3, because 3 independent rows. So that's how I got the repeating value is 3. So rank is equal to the rank. All right, very good. So I have my P, and what's my Q? My Q is whatever is sitting under P. That's my Q. And I don't care about these 2, these 3 and these 2, I don't care about. Why not? Just one second. You may remember that I also have this R and S. This is a different R, residual R type thing. So this I don't care about, because in this, what I'm going to do, this R and S is not going to play any role. So therefore, I'm not worried about the other piece. Right? P and Q. So what do I have to do next? Exponent matrix. So this is exponent. How do you do that? You take this P1 and ask Wolfram alpha to invert it. If you are lazy, then you have more chances that it will do it correctly. You do that, and you have to be very careful about multiplying in the right order. So Q has to be before P inverse, and when you multiply it, you will get this segment. You will get this segment. Now, this is very important. What are these 3 things? Because you have to label them. You got a matrix, but that's not, you are not really done. What you have to do, you have to, oh, by the way, and then you have identity matrix. So therefore, do you see 1, 0, 0, 1? That's your identity matrix. So you have just made this matrix. But how do you label on the top? The way you label on the top is, do you see that when you did the P, it was T, K, B, H. T, K, B, H are the 3 things I have written on the top. And whatever was the Q matrices R and EB, I have written R and EB. It's very important because if I took something else for P, then I have to take those variables and write it as first three elements. Alright. So now is the magic. So you see, take this line. These are really the eigenvalues. If take this line, let's multiply it out. Multiply it out, and whatever I multiply it out will be my pi 1. So what will be my multiplication? T to the power minus 1. First term, you see, T to the power minus 1. KB to the power minus 1. I should have written KB here, but you see, KB is downstairs. I should write H bar, but anyway, it is because of 2 pi. But you have 1, so therefore it should be in the numerator. R is on the numerator also. And 0, e to the power 0, so I don't have that in here. That's my first collected variable. And my second collected variable, remember I'm supposed to have 2 scale variable. What this would be? It will again be T inverse, which is that, KV inverse, which is that, and then I have 0, doesn't count, 0 doesn't count, and EB, I have an EB over here. So these two are my scale variables. If I want to do any experiment, I have to change EB and T simultaneously, because that will give me the same point. The procedure is clear, right? And you can check that. I mean, essentially what I'm doing here is essentially writing this A is minus 1, B is minus 1, H is 1, and that's how you will essentially get pi 1 and pi 2. So actually what you are doing is not very complicated. What you say that because it has to be dimensionless in here, you are writing this procedure about doing this is really a way of finding what combination of T, KB, H and R and EB with coefficients, with various unknown coefficients will give you dimensionless combination of parameters. Right. Yes?
If you consider the 3 rows in the middle, for example.
Yes, that will also work. Let me show you another one. So I'm going to show you in a second. So therefore you have your variables pi 1 and pi 2, and Buckingham said that it's going to be a generalized new thing. Instead of depending on this 5 variable, it will depend on the 4 variables now. 2 variables now. You can write it in this form, or you can push it one in one side and write it in another form. Now in this one, it is telling you what your x and y axis should be. This should be your y axis, and this should be your x axis. Then you go to the lab and start doing the measurement. Because you don't know what the result is going to be. It may be exponential, right? That's what Arrhenius found. Arrhenius found there is exponential degradation. But it is telling Arrhenius what to go and do in the lab. Not to go randomly dial on the temperature. Now, one thing is that if you assume that H bar is absent, remember I had 5 unknowns, and let's say you don't know, you're before quantum mechanics, you don't know H bar. If you don't have H bar, it will still tell you that you need a something of the magnitude of H bar or dimension of H bar for this to work. Because otherwise you cannot have 2 independent ones. So it will make sure that when you get the second variable, you have to have a C that is a dimension of H bar. You don't know the meaning of H bar, but it must have, in order to get it dimensionless, you must have something over there. Right? Now, in some way, that's not complicated. You know, it's like H bar omega and KT. So, e to the power H bar omega. At any time you have omega over KT, it cannot work. It has to be there. It has to be H bar. Otherwise, it's not dimensionally correct. And e to the power, on the top, you cannot have any dimension variable. So, therefore, it immediately tells you that that combination must work. And in fact, it turns out the first time Planck did his famous curve, he did curve fitting. The night before, he saw the data the previous night, and in the morning, he was in a conference, in the morning, he did a curve fit of the 2 sides. And then it fitted so beautifully that for the next 3 months, he tried to come up with hypothesis that what it could mean, this quanta and other things. It took him 3 months to get a derivation, but he did not believe in that derivation. That's why until Einstein came, the concept of photon did not exist. Although in Planck already has h bar omega, but he doesn't believe it. He thinks it's a fitting thing. So it's very interesting how fitting, brave fitting helps you in doing good science. Don't overfit, but fit. This is your example, right? I knew you will ask this question. So, no, I did not know. So, what is this variable? This is called P. And I have these two things, two segmented part, which will be my Q. So, do you see that? I have the Q written in here and I have P. It's another P. You do the same thing. You do the P inverse, but this time you do the P inverse this way and then you do the Q. And you make, remember that the way you have written P, T, K, B, R. So you write T, K, B. I should have written an R. I've copied it wrong. And this is E, B, and T. So E, B, and T. And you can correspondingly find out another combination that will also work. But you see, instead of E over K, B, R, T, you have this one. I need to double check I think I may have copied it wrong. But, hey, why don't I assign it as a homework for you? No, I'll double check. But it has to come in the same way. And it turns out that these variables, the new variables that you have, actually, if you did because this looks very different from what you had before. But if you take these new variables and divide, you will get back the origin. Because this is two different things are dimensionless. You divide it, you get the old result back. And so therefore, and then you can correspondingly get the old second one also back. And so you can get back the same expression. It is just a different way of sort of writing the same equation. And then you go to the lab and do the measurement. And if it's a straight line of this sort, let's say on a log plot or something, then you know what the function is, what f is. F comes from experiment. Or if you have a differential equation, f can come from the differential equation also. But if you don't have a differential equation, f will come from either interrogating the web but the variables better be these two. This is a homework problem that you will do, but let me solve that Hoynes problem, that how Newton in some way can anticipate Einstein's result, right? So this is very strange. How does Newton know that light can bend next to a massive galaxy? How can he know that? You don't have to know anything, yet you can answer this question. We know what the general issue is, that assume that there is a light from a star coming in, and if this is sun, then the sun is so massive that if the light passes close by, then it can bend the light. And so during, eclipse, and then what you can do when this is completely covered, you can see stars from the back of the sun, right? This is all gravitational lensing, right? Now, this idea that the space-time is carved and all, Newton, of course, did not know any of those things. But let's say you are in Newton's shoe and you say, well, let's say the light bends. This is your hypothesis, light bends when it comes close to the sun. I don't know how it bends, what the physics says, I don't know. But it depends on how close the light is to the massive body. That seems reasonable, right? Because if it's close to a massive body, maybe it bends more. Hypothesis. And maybe it depends on how massive the star is. Maybe. So therefore, you can write it in the Buckingham PI form, R, M, and theta. You can write the Buckingham PI matrix. But it turns out, if you just assume this determinant is 0. So the problem is not completely specified. So you are not done yet. You have missing something. So you go back to your drawing board and do something what Newton did. He said, well, I think it may also depend on the gravitational constant g. It may depend on the gravitational constant g because it's pulling something, maybe. It may also depend on the velocity of light. Maybe that because moving at the velocity of light, maybe velocity of. So you have, remember, in one afternoon, you can test out 10 of these hypotheses. No problem, whichever one works. Then you write out this matrix. Do you remember that in this case, I have M, L, and T. I did not write the temperature expression is because temperature doesn't enter in this problem. Of course, if I put one temperature in here, it will come. But I have not put it in, so therefore I need out of the 7, I just need 3. And how many variables I have? I have 5. So I have 5. Theta, R. By the way, this theta is the deviation, how much the light bent because of this. And then I have R, I have M, I have G, and theta G is the gravitational constant. And you can write out the matrix. So theta is dimensionless, it's radian. So many radians it bends. So therefore, it does not depend on MLT, any of these things, right? And R depends on only length. R is the distance, is the length. M depends on the mass, and so on and so forth. You can just check it out. The dimension of gravitational constant. C is the velocity of light. What is that? Centimeter per second. Centimeter per second. So again, you do that same thing. Number of unknowns is 5. Rank of the matrix, you put it in, is 3, and you have 2. And then you have the repeating variables is the same as the number of rankings. Right. So then you go through. I will not make life difficult for you. You get the idea. You have Q1 and P1. I have a comment on this in a second, but just for the time being, I say that this is P1 and this is Q1. And you do this thing, you can see that the last two variables, which are theta and r. Remember, Q has now is in here on the top side. So my theta and r has moved in here. And my M, G, and C, my M, G, and C has moved in the beginning because that's the P, right? Then what do I have to do? That already gives me the answer. Because I'll have to, if I go along this line, I will say theta to the power 1 and all of them equal to 0. So my first dimensional variable is theta. Fine. That's dimensionless. So that's no-brainer. But what about the second one? The second one says that m to the power minus 1, g to the power minus 1, c square, a, and theta to the power 0, r to the power 1 gives the second variable, or c square r, gm. You can begin to see already what's going to happen. That you are saying theta, the quantity you want to calculate, must come as a function of this quantity. And this function of this quantity, you can take this quantity or inverse of it, doesn't matter, because both are dimensionless. So then if you do that, this answer, gm divided by r, gm r divided by c square, is off by a factor of 2 from Einstein's result. And the reason is, given this combination, there is no other way that the system can behave. Now remember, this is f. So therefore I don't know whether it is sine gm over c square r, or whether it is e to the power gm over that I don't know. That requires Einstein, and that requires real measurement. But that it is this combination, nothing else is necessary. Now in here, there is something I did, a trick. You have to be a little careful what I did. Remember, at the end, I wanted my answer in terms of theta, because I wanted to write theta something. Anytime I want an answer in terms of something, it is better to put it in the Q matrix. Because Q matrix, wherever the Q matrix is, it will come as unit. So therefore, it will be immediately allow me to get my output in the right form. And that's what previously I also did. I wanted to get the degradation rate, R. And so I put the Q matrix where there is R. So that is a trick, but if you do it in any other combination, that will also work. You get the idea, right? Basic idea. And so if somebody had to do an experiment, they should plot y-axis should be theta, and x-axis should be gmc square over r. And then c square is a constant, g is a universal thing, and so therefore for different star, the m could be different. And you have to see how close it is coming to the sun in order to see how much bending it has. There are many examples, and in fact, the only way mechanical engineers survive is because of this theorem. Because by second year undergraduate, they know how to use it. because the differential equations that it's not like our diffusion equation. Our semiconductor solid state is really easy compared to them. So in that case, they have no way of actually solving the full problem. It cannot happen. And so they do everything in this way, and then they experimentally determine the function. So they have big tables in which the function f is determined. So let me explain to you why it works. It sounds like a magic. I don't know any physics, and yet I am sort of anticipating different types of things. Why does it work? So the best way, when you want to understand something, why something works, the best way to take something that you already know and work it out in a different way. So frankly speaking, until this weekend, I did not really care about that, but because I know how to use this thing, but because I have to come to this class, so therefore I sat down Saturday morning and I worked it out that why it works. So this is how it works. Assume that you have that equation. You all know that equation, right? It's a diffusion equation, and you have its recombination there, and so on and so forth. And you know what the solution is. But before you know the solution, I think you can use the scaling method in the last class. N naught, n star, scale variable. I'm following last class thing. And then you have to insert it in here. And then you have to cross multiply. And then what the next thing you do? You take all this and make it 1. Right? And when we do that, then we know the scale is x naught is square root of d tau. That's what you know. Let us say I don't have that differential equation. Oh, let me continue first. Then I have that equation. What is the solution of that equation? Well, you all know that. It's n star e to the power x and b e to the power minus x. You can insert it in that equation to see that this equation will be satisfied. Of course, a and b you get from your boundary conditions. You get that from boundary. But you know the solution. And of course, after you know the solution, you can insert the value, because remember, x is equal to x naught x star. So wherever you see x star, you divide by x naught, and x naught is square root of d tau. So yeah, that's the same expression. But do you immediately realize that actually the fundamental variable in the system is really x over d tau, square root of d tau. That's the controlling variable. And so this is your y, quote unquote y of your experimental axis. And this is your x divided by square root of dt, that's your other axis. That it happens to be like this, maybe in a transistor it happens like that. If you have just illumination, this may look like that. You may have different things, but the variables has to be this, for sure. That, right? So if this is how it was done, but let's say I do not know the diffusion equation. I don't know it. I want to use Buckingham PI Theorem. And let's see how far I can go with that Buckingham PI Theorem. So it's you see that what are my variables now? N, one variable, because I know that I'm looking for a diffusion of something. X, it is diffusing in space, so I'm thinking that this problem may depend on N, it may depend on X, it may depend on diffusion coefficient, it's diffusing, doing something, I don't know how it's diffusing, and it depends on tau. Because it's recombining after a certain time, I make an assumption that it is tau. Now, for a second, I'm forgetting about this. I'm just saying that this depends on 4 variables. So I can write the matrix, right? I can write the matrix in terms of MLT. I could, if I wanted, I could write all the 7 variables. But in this particular case, you can immediately see that M does not matter, because none of these equations have M in it, mass in it. So therefore, I can immediately throw that out. Why carry it around? But if you wanted to carry, that's no problem. You can do that. But why carry a dead weight around? So now what do I have to do next? Remember what I'm after. What is my output variable is going to be? N, right? I want N to N in terms of something. So why should I put my Q matrix somewhere here? So it turns out there are 4 variables. If you do a rank of this matrix, you say 2. So how many scale dimensions am I going to have? 4 minus 2 is I'm going to have 2 scale dimensions. That's pi 1 and pi 2 is what I'm going to get. You sort of already know that one of them is going to be x divided by square root of dt. That's going to be 1. and another is going to be n divided by n naught. That's going to be another. So you sort of can already see what's going to happen. So you have the Q1, right? Q1 is the first two rows I have taken, and you have the P1, the next two rows, and then you look at that and you write out the pi 1 and pi 2. Let's work it out. Pi 1 has n to the power 1, x to the power 0, d to the power 1/5, and tau to the power 1/5. Now, does it make any sense? Remember, d is centimeter squared per second, tau is second. So therefore, the unit of all this is centimeter cube, and density is number per centimeter cube. So this is dimensionless, and that gives you a scale for n naught. N naught should be on the in terms of, but the most interesting thing is this one, because it says x to the power 1, d to the power half, q to the power half, and that is exactly the variable that you need. So how is it possible that this equation knows what the answer is? Can you see what the trick is? How this one knows that this equation, I don't even know this equation, but yet that this has to be the variable. The reason is, I'll just give you a hint, that the second you said that there is something called a diffusion coefficient, you immediately have said the system has a second order term in there. You don't have to know what that term is, but the second you have said there's d, you know that there is a second order term. The second you have said that my solution depends on tau, you know that there is a zeroth order term sitting here, right? So therefore, the second I know what my variables are, and the second I know what the other variables are, it immediately defines, you may not see it, but it defines underlying system that is sort of trying to come out of those variables. That's why the method works. So therefore, the bottom line I want to say that you don't have to know what the system is. You can just first do this and then go to the lab and then do the measurement, and then you can, when you do the measurement, then you will get the right functions that will come out of the measurement. It can be from big data, it can be from small data, whatever it is, you will be able to get the F. And it turns out all this machine learning big things that you see, that is really a way of calculating F. What the function is. You have input and you have output, and you will collapse the input in a particular combination like this. And then when you're doing a physics problem, not the Facebook users problem, when you are doing a physics problem, then you'll collapse a variable. It may look like you have 10 variables and 10 output variables, not like that. You have to collapse it using the scaling theory to a fewer variable, and then you collapse the output to a fewer variable. All of a sudden, your 152 layers will become a tiny layer that you can train very, very quickly. So that's the physics, right? So it turns out that fluid mechanics people, they used it extensively because the equation there is a highly nonlinear equation, Navier-Stokes equation. That's how the wind tunnels work, because wind tunnels is all about scaling. That if your wing length proportional to the velocity of light has a certain combination, it doesn't matter whether you have a tiny aircraft or you have a jumbo jet flying. The physics is the same. And this is because they have all relying on the same scaling curve. So if you go to the Wright brothers lab, they were beautiful scientists because they were the first ones to build a tiny wind tunnel. If you go there, there's a tiny box over there that which you can, they were testing with different types of foil, the shape and other things, and how the lift and the drag and other things happen. So they did not know all this, but nonetheless, they understood the essence between a small plane and a big plane. So next time you are you should go. It's very close, 2-3 hours from here. It turns out that in fluid mechanics is full of this dimensionless group. The whole fluid mechanics thing, you have Reynolds number, you have Mach number, velocity of something with respect to the velocity of light. And you have all sorts of combination of numbers as you want to solve different types of problems. So different scientists have come at different times, have made different assumptions about different problems, and they have come with these variables. So next time you they'll be impressed if you tell the mechanical engineer that you know how to do Buckingham PI, because electrical engineers are not supposed to know. One of the most interesting thing about all this is that you'll often see that that in many systems are dimensionally similar. So things that move, so planes, for example, the mass as gradually have grown over the years. And you have jumbo jets, and nowadays maybe there will be an 18-hour flight between, I heard, between Singapore and Chicago or something. This will going to be the longest flight. And it turns out that despite all this, if you look at the size of the engine and size of the thing that it can lift, it has absolutely a scaling relationship. Because once you sort of scale it in properly, then it will have. So therefore, what they are saying that m divided by this m is a constant. That's the dimensionless value, right? When the two things are, these are independently, they have dimensions, kg and kg. But if you divide it, then it has to stay in the same line, and that's your function f. And it turns out that, the exact relationship is me is 0.13, m to the power 0.83. So the 83, you can view it as the 1, let's say. This constant dimensionless analysis cannot give you constants, but it can tell you that the relationship has to be this. In fact, there is a clean derivation of this. I'll show you in the next time. But the point is that this is not only true for planes. It turns out that whether you have a running mammal, or you have a flying bird, or flying bats, and flying insects, because they are all trying to fly, and therefore they all have the same physics. And so this is the body mass, and this is the velocity they can reach, and once again this scaling relationship. Do you see the order magnitude? We are talking about 12 orders of magnitude in terms of mass, right? And steel is more or less, there are some variations of course, but more or less. And then of course swimming is different, because swimming is in a fluid which is a dense fluid. Air is different, right? So therefore these two have different scaling laws. So very powerful to do experiments, helpful for doing experiments. So let me conclude by saying that the reason it works fundamentally is that, let's say you are in the solar system, you are doing some experiment using the units of meters and, second and all. And think about another XYZ person, 500 light years away. That person is also doing the experiment. Now that person is certainly not using meters and seconds and all. They have their own unit. Maybe they are using some other form of units. But the thing is, the law of physics cannot be different in these two places. So therefore, all laws of physics must be written in the dimensionless form. Any law of physics that has dimension in it is local. Meaning it's a car fitting. But any general law that holds broadly across the universe must be dimensionless. And that is the fundamental reason this type of thing works. It has to be non-dimensional. The second was, but my main point in this lecture was to say that the number of variables in an experiment, we want to reduce it. Remember, this is the course about experiment. It's not really, I'm not interested in the other things, how to reduce the number of experiments. And many applications, fluid mechanics, phase transition, percolation theory, uses it extensively. And so therefore, if you do some of these things on your own, one afternoon is all it takes in order to do things, try out different things. And in terms of the issue is that you may not have defined enough variables, or you may have defined too many variables. For example, the mass. If you say light bending next to the sun depends on the mass of the earth, dimensionally it will be okay. It will still, but it has got completely wrong thing, right? Bending of the sun. So therefore, you still have to need to know a little bit of physics. You cannot be totally ignorant. But once you know a little bit of physics, you can run with it for a long time. that's the goal of all. Now in the next class, I'm going to do Fisher's work. Fisher's set of design of experiment, randomization, and overtest. Those will come next. This is sort of the foundation on which this. One thing is that the way I am presenting it, it's as ahistorical. Meaning I am explaining it the way easy to understand perhaps. But Fisher did not know about this. But had he known that, his work would have been much more easier, right? So that's what.